Determine algebraically whether the functions in each pair are inverses of each other. Verify the answers to part A graphically. So in A, algebraically, that's where you switch the x and the y and solve for y. And so if I started with y equals 3x minus 6, and I wanted to find its inverse, I would switch the x and the y. Solve for y, add 6 to both sides, and divide by 3. X plus 6 divided by 3, is that equal to x minus 6 divided by 3? No. The equations are not the same, so they are not inverses. If the equations were the same, they would be inverses. Now we have to be a little bit careful here, okay? Because right now, it's pretty easy to see that they're not the same. So we can say no. No, they are not inverses. Sometimes you have to do a little bit of algebraic manipulation so the equations look the same. For example, in this first one, y equals x plus 6 over 3 is the same as y equals 1/3 x plus 2. Could you do that algebraic manipulation to make those match? What did I do? I divided the x by 3, and I divided by the 6 by 3. The x by 3, well, dividing x by 3 is same as multiplying it by a third. 6 divided by 3 is the same as 2. For part B, algebraically, y equals negative x squared plus 3, and then they tell us it's a restriction on the domain. Only the positive part. So now if I switch x and y, switching x and y would mean I'd have x equals negative y squared plus 3, and my restriction would get switched as well. I need a restriction so that the y values are only bigger than or equal to 0. Now getting y by itself, so I could have y squared equals negative x plus 3, square root both sides. Would give me y equals plus or minus square root of negative x plus 3. But since we were told originally there was a restriction of x being greater than or equal to 0, that means on our inverse there has to be a restriction of y being greater than or equal to 0. The only one that would do that is the positive one and not the negative one. So since y is bigger than or equal to 0, my equation would only be the positive one. Does negative x plus 3 match up with 3 minus x? Yes. So there, they don't look the same to begin with, but a little manipulation would make them the same. Negative x plus 3 is equal to 3 minus x. So we can say right here that yes, they are inverses. In part B, it says verify your answers graphically. So for part B, I'm just going to scroll up here, start this on a new page. Y equals 3x minus 6. That's a line y-intercept at minus 6, a slope of 3, so I can go up 3 over 1, up 3 over 1. This would be the graph of y equals 3x minus 6. When I try to graph the other graph, y equals x minus 6 divided by 3. Or if you wanted to rearrange that to y equals mx plus b, we already talked about this being 1 over 3x minus 2. What would that mean? That would mean my y-intercept is at minus 2. I have a slope of 1/3, up 1 over 3, up 1 over 3. How can I tell graphically that these aren't an inverse? Well, if I had 0, negative 6 on my blue graph, on my inverse graph, I should have had negative 6, 0. Is that point on my green graph? No. Similarly, another point I have on my blue graph is 2, 0. Do I have 0, 2? No. You might even say it's quite obvious that the blue graph is not a reflection. If you reflect the blue graph over that diagonal line, it does not match up with the green graph. So that is how you could verify something graphically. I'll leave the verification of part B, where you graph both A and B. The only thing I'm going to help you in part B is I'm going to rewrite this second equation like this, and then say it isn't in factored form. So it has a horizontal reflection and a translation 3 to the right. In part A, the restriction on the domain means that you only draw half the parabola. And then from there you could verify it graphically. 7, 8, 11, and 13.